Welcome to this video series on probability, and in this first part we're going to discuss some basic definitions and look at some basic examples as we hope to build into more deeper concepts of probability in the next sets of videos. So the term probability refers to the measure of uncertainty or likelihood that an event will occur, and it's expressed as a number between 0 and 1. Like we have an example, the probability of flipping a coin and landing on heads is 0.5 or half. We also have another term called experiment. So it's the procedure or process that is carried out under specific conditions to observe, measure, or record the outcomes. And it's important to note that the outcomes may vary under certain conditions, even if the experiment is repeated. And another term is a sample space, which is the set of all possible outcomes of an experiment. And in the example of a towing course, our sample space is comprised of heads and tails. Another term is event, and an event is just a subset of the sample space. It's just part of the sample space. And in the case of having one die, when we roll, we have an event of having even numbers being 2, 4, and 6. We compute probability by having the number of favorable outcomes divided by the total number of events. And here we have an example of rolling a die and landing on a 4, which will be 1/6, which is the total number of events in a die. So some terms also in respect to events, we have independent, dependent, and mutually exclusive events. And we say two events are mutually exclusive if they cannot occur at the same time or simultaneously. And if we have events that the occurrence of one affects the occurrence of another, now we refer to that term as dependent events. But if these events do not, such that one event does not affect another, now those events are independent events. We also have some rules of probability, 3 common rules of probability that we'll see even as we go further in this video series. The first one is addition. So if we have mutually exclusive events A and B, now the probability of the union of the two events, what's the probability of A union B, is equal to the sum of the probability of A and B. So probability of A union B is equal to probability of A plus probability of B. But if we have independent events and we want to find the elements that are both in A and B, so the intersection, so we have the probabilities of A and B being equal to P of A intersection B, which is given by P of A multiplied by P of B. The other rule is the complement rule, and it's just like the opposite of the event occurring. So the probability of the event not occurring is 1 minus the probability of the event occurring. This is because all probabilities add to 1. As we said, it runs from 0 to 1. The final term that we're going to define in this first series is conditional probability, and it's stated as the probability of an event A given another event B has occurred. So we are conditioning an event given that another event has occurred. And the conditional probability for two independent events, so B given A is denoted by this symbol, so P of B given A, and it's defined using the equation here below. So probability of B given A is equals to probability of A intersection B divided by the probability of A. And it's important to know that A intersection B is as in the previous slide where we had the multiplication rule. So it will be given by probability of A multiplied by B and divided by the probability of A. Something to note when dealing with conditional probability is for mutually exclusive events, and this means events that cannot occur simultaneously, the probability of A intersection B is given as 0. So if we have the numerator as 0, therefore the conditional probability B given A would be 0. Some areas where we apply the concept of probability include business and finance, where we look at things like the customer behavior, predicting the churn rate, the probability of purchasing trends. Also, we look at healthcare, where we see the probability of a pandemic or assessing the effectiveness of treatment. We also have climate and weather, where we see things like the forecasting of weather condition, what's the probability tomorrow it's going to rain. And the important part is artificial intelligence and machine learning, and this we'll be seeing towards the end of this series. We have probabilistic models such as the Bayesian networks. So some few examples as we end the first part. We have this example 1. A single card is drawn from a standard deck of 52. What is the probability of drawing a red card? So a picture here showing the cards, and we have 4 sets. We have hearts, diamonds, clubs, and spades. So these are club, hearts, spade, and diamond, and each of them have 13, leading up to 52 in total. So the red cards are represented by diamond and hearts, which in total now will come 13 plus 13, giving us 26. So the probability of a red card will be 26 divided by 52, half, 0.5. The second example, we have a jar with 5 red balls, 3 blue balls, and 2 green balls. A ball is randomly selected. What is the probability of getting a red ball? And also, what is the probability of getting a blue or green ball? So in the first example, it's just straightforward. So you just take the total number of red balls divided by the total number of balls. So, total red balls divided by total number of balls, so giving us half. In the second one is now we have OR, and OR indicates at the additional axiom of probability, so it will be just with the probability of blue plus the probability of green, which will give us 3/10 plus 2/10, giving us half. The third example, we have 30 students, 18 liking cricket and 12 liking football. So what is the probability that if one student is selected randomly, they like football? So here will be just the total number of students who like football divided by the total number of students in the group. So it will be 12 divided by 30, which will give us 0.4. The final example that we have here, still the same example of the deck of cards, but now we are drawing 2 cards at randomly without replacement. So the concept of without replacement we'll discuss in the second part of this series. And what we want to see, what's the probability that both of these cards are S's. So the solution, we have 4 S's in the standard deck of cards. So we are selecting, when we select without replacement, it means that the total denominator changes in the second drawing. So in the first, we'll have 4 divided by 52. Remember, we have 4 S's in the standard deck. And then in the second one, now we are left with 51. Remember, we have 1 less S, and therefore our total S's in the second example are 3. So giving be 3/51. Now to answer our question, we remember we have the probability that both are S's. This now we apply the multiplication axiom, and therefore we'll be having probability that both are S's will be 4/52 multiplied by 3/51, and it will give us 1/21. So that comes to the end of the first part of our series, and I hope you liked it, and I'll see you in the next series.